Hello and welcome again. In this video, we'll talk about an implementation of the Miller-Rabin primality test and some of the techniques that are actually used to do the implementation. Now, if you want to implement a decent primality test, for example, using Java or any other programming language, these are some of the techniques that it will be used. So the first one is you want to rule out small prime factors from the prime that you're testing. Let's say, for example, you test whether the number p hat is divisible by the first 100 primes. Now, this is a good idea because you don't want to waste a lot of power if you already know that the number has a small prime factor. So you immediately will know that it's not a prime just by doing division, which is not as expensive in terms of computation as the other things that we're going to do, like modular exponentiation and stuff like that. So you want to do that. Actually, the implementation of Java of primality test, which Java has one, I believe they check the first 50 primes. Although I'm not 100% sure of that, but they check some of the first primes. So basically, they check some primes, the first primes, and that's why it's a good idea just to rule out something that is obviously not a prime because it has a divisor which is small. Now, remember the Miller-Rabin algorithm. We choose an A uniformly random between 2 and the number -2. Instead of doing that, we're gonna usually the implementation will use specific values of A instead of choosing them at random. What you usually want to do is you're going to choose A to be a prime number. That reduces a little bit of computation too. And if you were to implement this in programming language, you will do 1 and 2. So you will rule out the first primes, and then you will use the Miller-Rabin primality test. And also, once you know that it is prime or is likely a prime, and this test gives you it is likely a prime, then you will use another method for primality. Of course, we haven't discussed any other method. The only one we had so far is the Miller-Rabin primality test. And of course, there are many others. So basically, what a programming language like Java will do, or some other program, or an efficient way of checking that something is a prime is an implementation using these 3 ideas and maybe a little bit more. But these are the basic ideas that people will use. Okay. So let's talk about the implementation of the Miller-Rabin test in Java. So in particular in the programming language we are using in this course. So as I mentioned earlier, the input for the Miller-Rabin algorithm is p hat, the number we're trying to check whether or not it's a prime, with this decomposition. And of course the security parameter it adds. I mentioned this before and I wrote it down here. In reality, we should only need p hat and s. Because this implementation, you should be able to get it from p hat. So this is what it says here. The implementation should obtain this composition p hat -1, 2 to the u, and r. So basically what we're looking for is the value of u and the value of r. U here is the exponent of 2, the largest power of 2 that goes into p hat -1, and r is an odd number. If you were to really implement something that is good, that doesn't need from the user the security parameter. Let's say the user doesn't know anything. So you could also do that because there are ways. Remember earlier I discussed that you can compute the security parameter from the bit length of p hat, and there was a chart over there. So basically the user will only need to enter the number that needs to be checked, which is usually what you expect the user or to do. So, but for now, let's keep the p hat and s. So, how do we get this u here? Now, you can get it in Java very easily. You can do a while loop, and the while loop could go like this. I start with this number. I divide it by 2. If it is divisible by 2, which should be because it's an odd number, an even number, then I make a counter of u equal 1. And I consider the number p hat -1 divided by 2. If that number itself is divisible by 2, I increase the number u by another just one increment. increment of 1. And I keep doing that until that number that is here, which is this, dividing by 2 several times, is not divisible by 2 anymore. I just told you more or less what the pseudocode will be for that. So that's one way to get the U. But there is a much easier way to do it in Java. And Java has a method that allows us to compute that in just one line. So the exponent U can be obtained easily using this. You put the number p hat minus 1 here, and you said that get lowest set bit, parenthesis, semicolon. This line of code that is here, of course, this has to do with the lowest bit there. But basically what that's doing is, if you have the number written in decimal, that will give you the exponent here, or the largest power, the exponent of the largest power of 2 that goes into p hat minus 1, or whatever number you put in here. So you can put whatever number is here, and that will give you the largest power of 2 that goes, the exponent of the largest power. And this works for big integers, and the output of this will be an integer. So this method, let me just scroll up again a little bit. This method returns an integer type. So it's very easy to do. So you could do a while loop to get this exponent U, which is something easy to do in Java also. But Java has this nice method here to allow us to compute that exponent U there. So what I'm going to do is I'm going to move to Eclipse, and I will show you how that works there. So I will see you in Eclipse. So I'm here in Eclipse, and I will show you how the this method get lowest set bit works for computing the exponent of the largest power of 2 that goes into any number. It could be in particular for p hat minus 1. So as you can see here, I already imported the java.math.big integer. So I'm gonna define big integer number here, or big integer object, which you remember you define it like this. You type big integer, and then whatever the name of your variable is, and then new, and then you say big integer, and whatever number you want to type in here. Now, if you want to read this from the console, well, you just read it using the scanner. So in here, so what I'm gonna do is I'm gonna, for this number that I have here, that's a variable number, I'm gonna compute the exponent of the largest power that goes into this number here, this whole number. So what I do is basically just this, the output of get lowest set bit, that the output of that is an integer type. So that's why I have an integer type there. I'm gonna put that exponent in a variable which I'm gonna call exponent, and then that's gonna be equal to whatever the number that I have here, which is a big integer, that, and get the lowest bit, parenthesis, semicolon. That will just give me the again, let me say that again, is the exponent of the largest power that goes into whatever number you put in here. And I have a printout there, so just to see what that exponent might be. So let me just go ahead and do that. So I'm gonna save this, and I'm gonna run this. So whatever this program prints out, that will be, of course, what I just said earlier. So if I run it, I get 8. Now, what is this number 8 here? It means that if I go ahead and factor this number, this whole number here in yellow, that number is going to be equal to 2 to the 8 times another odd number. And it has to be odd number because that's what this get lowest set bit does. Computes the exponent of the largest power of 2 that goes into that number. Now, so that will compute that exponent. So it's very easy in Java to do that. You could, as I mentioned earlier in the video, you could also do while loop. You will get exactly the same exponent, but I think this is easier, of course. It's just one line of code. Now, how would you go about then computing the odd number? Remember, this exponent gives me the exponent. That's the variable u, if you remember from the Miller-Rabin algorithm. That's the variable u that we were talking about. And then we have to compute the odd number. So how will you compute the odd number? The odd number that it is there should be computed using this number, which is the number, and then I divide it by 2 to this exponent. I hope that's clear, because what happens here is this number, remember, this number that is here is 2 to this exponent times the odd number I'm trying to find. If you solve that algebraically, you will find that that's exactly what you need to do. So let me do that in here. So how do I get the odd number? So I have to take this number here, which is called number, and I'm going to divide it by 2 to the exponent. Now, because this involves division of big integers, so then I'll have to do a big integer division. The first thing I have to do is I have to take this number that I have here, my variable number, and divide it by 2 to that exponent. So the way to do that is like this. We're going to do just division of big integer types. So because I have to do division of big integer types, 2 is not going to be useful here as an integer. I have to define it as a big integer type. So what I have to do is I have to declare 2 as a big integer. So it's kind of a little bit annoying there, because I should be able to use it, but that's the way it's set up. So the way we're gonna do it here between the public class and the public static void, the main thing, I'm gonna declare a private variable that's gonna be 2, is gonna be integer type. The number just 2. So I'm gonna just type private static final, and then it's gonna be a big integer type. And I'm gonna give it a name. So let's say I'm gonna call it 2, just like this, 2, and it's gonna be equal to new. And remember, this is just declaring that variable there to use it later. So that's the number 2, basically what I'm doing here. So that's again big integer, and of course I have to type there whatever the number I want to define here. So that's gonna be, let's say, 2. So that basically what it's doing is I'm just saying I have the number 2 and it is a big integer type. The reason I'm doing that is because I need to take 2 to this exponent and take that number that is here divided by that thing here. So let me do that in here. So what I want to do is, of course, I need to get my odd number. So let's just say that I'm gonna type it here. So this is big integer, and integer, and it's gonna be an odd number. So let me just call it odd, and then that's gonna be equal to this number that is here divided by 2 to this exponent that is there, right? Because these are big integer types, I need to do all this in big integer. So this is gonna be odd. And then what I have to do is I have to take my number, whatever the number is, and I'm gonna divide it. So it's divide, and I'm gonna divide it by 2 to this exponent. So 2 is my variable 2 that I have there, 2 times, and power here will be POW, and then I have my exponent there, which is, well, very good, it's already there for me. So this line of code that I just typed here is going to compute my R, which, if you remember, that is the variable we saw earlier in the video. So at this point, of course, I have to print it out and see what it is. So I'm going to take this and I'm going to copy and paste over here. And I'm going to say just please print out for me that odd number. Okay. All right. So this should work. So I hope this was clear. I would love to have wrote down this a little bit more precise, but I hope you get this idea from this. So basically what I'm doing is I'm factoring this number here as 2 to a power or exponent, which is this one here that is computed with let, get, lowest set bit, and I'm going to compute the odd number. So it's 2 to the exponent times the odd number, which I call odd, which is done by doing division. I take my big integer and divide it by 2 to that exponent. So that's basically what happened there. So let me run this. So if I run it, I get 8, which is the exponent of a power of the largest power of 2 that goes into the number, and this is the odd number that multiplies that power of 2 what gives me the original number that is there. And you can see that it's an odd number because it ends in 5, so it's odd. Now, I want to actually prove to you that 2 to the 8 times this number that is here is actually my original number, the number that I started with. So let me go ahead and do that. So I'm going to copy and paste this 2 here, and I'm going to go to this fancy calculator. So that's going to be 2 to the 8 times, and I'm going to copy and paste this odd number that is here. I'm going to copy and paste here. So that's 2 to the 8 times this number. So that's the factorization I was looking for, is 2 to the u times the r that I have there. Once I compute this, I should get back this, let me close this. I should get back this yellow number that is right here. So let's go ahead and do that. So let me just evaluate this. I get this number that is here. And as you see, I'm going to copy and paste it here. Of course, Java Eclipse is going to give me an error here, but it's exactly this number. This number that this here is exactly the number that you see over there. So I got the factorization from this computation. Now you can, of course, change this number into whatever you want. It's a big integer type, so just type number there, and that will give you the exponent. So, for example, let's just try another one. Let's put another 0 there, for example. 2 zeros, 3 zeros there. I'm going to save it. Then, so I have 2 to the 11 times this number that is here. And if you, of course, if you do 2 to the 11 times that number, you will exactly get the number that is here. So these are the basic ideas that you need to know in order to actually implement the Miller-Rabin algorithm. The reason for that is because anything else in that algorithm is basically a for loop and an if statement, something that you already know how to do. So I'm gonna go back to writing, and because I have to explain a little bit more before I actually finish this. So I will go back to writing. So I want to mention a couple of things before I actually finish the video. So what we did here was we actually did this in Java, and we did more than that. We actually computed the odd integer. Now I want to emphasize a little bit more what I was saying in the video, because remember, p hat minus 1 is equal to 2 to the u times r. If you solve this algebraically, you can compute r like this. This is exactly what I was doing in Eclipse. I took this big integer type, divided by 2 to the u, and remember in Java I had to declare this 2 as a big integer so I can take this power here. So that's basically what I just did in Eclipse. Now there is one more thing I want to mention. I think I mentioned this already, but I'm going to emphasize that. I'm going to scroll all the way up to the algorithms, quite long, because we have done quite a lot here. So let's go all the way back to the algorithm here. I mentioned this in the algorithm, and remember when we were doing the examples, there was a lot of repetition of computation of these powers here, this modular exponentiation. So not to repeat this computations, what you can do is in here, before you actually go into the the if loop and this for loop here, just right here after you write down this for loop, pre-compute all of this. A to the p hat minus 1, or basically what it is a to the 2 to the j times r, where j runs from 1 to u. Pre-compute those things and put them in an array so you can make this comparison later. The reason I'm saying that is because you can still do this without doing that pre-computation. You still want to work, but you will repeat a lot of computations, so things here will repeat themselves. And just to avoid that repetition, just go ahead and compute all this a 2 to the j times r for j between 1 and u. This a to the p hat minus 1 will actually be 2 to the u times r, this computation modulo p hat. That will save a little bit of time when you do the implementation actually of this algorithm. So that's all I wanted to say. So just pre-compute them here so you save a little bit of time for the implementation of this in Java. So that's basically all I want to say. You have now all the elements to actually implement this pseudocode in Java. Again, as I mentioned earlier, you just have to just do the for loops, the if loops that are here, and these other for loops, and you already know how to do that. That should not be too complicated now for you to actually type it and then just get the program running well. So I'm gonna finish the video now, and so in the next video I'm gonna say a couple of words more about the RSA, and we hopefully we'll finish the RSA with the next video. So I will see you in the next video.